Hello everyone, this is Dooyoung Kim, a PhD candidate in the KAIST UVL lab. I'll begin my presentation on Edge-Centric space rescaling with redirected walking for Dissimilar physical virtual space registration. First, let's start with the background of our research. Most VR devices currently define only an empty space as a playground, where users always have to stand up. In this case, users cannot utilize additional furniture in their space. So we wonder, is it enough to register a virtual space to the user-defined empty space? So we set our research goal as, how can you register a virtual space to the user's dissimilar physical space, where users could utilize their physical geometry in VR? Now I'll share our approach. Assume a user in a green track physical space connects to the target virtual space on the right. To achieve this, we extract the space's floor plan. Then we label basic geometric information for interaction, horizontal surface, obstacle, and floor. From this labeled floor plan, if we apply a single pair of relative translation gains, RTGs, in redirected walking, resulting in a change like this. One step further to align the edge of this horizontal surface and the spatial information more precisely, we divided the space into 9 grids with the main interaction horizontal surface from the space. And by applying RTGs to each grid, we can adaptively transform the space around the central collaborative object. As shown through slides, we propose the Edge-Centric space rescaling technique, which divides the space around the main interaction object, sets proper space rescaling constraints within the threshold range, and applies linear smoothing between grids to prevent sudden gain changes. We used our previous research results to apply threshold based on spatial configuration and linear smoothing for 0.5 meter between each grid. Now we need to apply our space rescaling technique for physical virtual space registration. We want to optimally rescale the physical space to match it to the target virtual space. So we need quantitative metrics for objective function for optimization. Previous research have used two metrics, register space size and semantic match ratio. However, when aligning real and virtual spaces, the ability to use interaction horizontal and vertical planes is crucial. Various studies have already shown that the ability to physically touch objects in VR can enhance the sense of presence. Moreover, in a VR table tennis scenario, immersed users may try to touch the virtual table, potentially leading to fall accidents. So we must consider how well the horizontal and vertical planes are aligned. Therefore, in this research, we proposed additional two components. First is horizontal edge match ratio, which could measure how well the horizontal edge of a physical object is aligned with the target virtual object. Second is the vertical plane match ratio, measures how well the vertical plane between physical and virtual space is aligned. Now we're ready to design experiments to validate our RTG grid method with previous spatial matching methods. 1-to-1 scales indicate spatial matching without any spatial modification effect, and RTG single indicates rescale floor plan with single RTGs. Under the MR telepresence scenario, we generate host and client spaces from rear rooms. This is the host space, which is specialized for XR telepresence meeting. And the VR client space includes XR labs, meeting rooms, as well as typical home and office spaces. We conducted evaluation on these spaces by pairing target virtual space with each tracked physical space. So we have 4 physical virtual space combination from rear rooms. For the MR telepresence scenario, we assumed the table and the wall as the main interaction object and conducted the experiment to validate our method with 2 previous approaches. We conducted an optimization algorithm, and the results confirmed that our method aligns table's edge and walls most effectively, and aligned space size was consistently the largest under all conditions. This figure visually represents the aligned results, where green indicating the aligned table's edge and walls. The orange area indicates the matched table plane areas, and red areas indicate semantically unmatched area and matched obstacle areas. As you can see, our approach could align more edges and wider space compared to other methods. Now we validate our spatial modification skill is beneficial for registering dissimilar physical virtual space. Now let's move on to the next page. Since the spatial dissimilarity between physical and virtual space goes higher, it's hard to register two spaces. For a more structured experiment design, we introduced the advanced version of spatial complexity and spatial dissimilarity. We start from the CE term from the 2021 TVCG paper, ARC, which could express the spatial complexity quantitatively. It has strengths in reflecting object density, but if object density between two spaces is similar, it will yield similar complexity values even if the layout or space size is different. To enhance this term, we utilize a qualitative approach to spatial complexity from our 2022 TVCG paper. Following the spatial complexity and the distribution of objects in the space, we introduced an object scatteredness component to measure the dispersion of objects within the space, and it can be expressed as the following formula. Based on the object density term from ARC, we added space size and spatial layout to create a spatial complexity term that accounts for all these factors. We can determine the spatial dissimilarity between spaces using the calculated spatial complexity ratios. Moreover, we go a step further and define a spatial matching difficulty. This is because in most VR scenarios, the main interaction object is set as 1, and users primarily utilize the register subspaces. So when we conduct the spatial matching, it is necessary to consider the target surface's size ratio between physical and virtual space. So in evaluation 2, we validate our spatial complexity and dissimilarity term with previous methods from ARC and ENI. While getting the ground truth of spatial complexity is challenging, we present the failure case of other approaches, while our approach robustly outputs proper values. Results from XR Studio and Meeting Room can be an example to validate ours with ARC's approach. Results show that since XR Studio and Meeting Room have different spatial configuration, ARC couldn't show significant differences, while our approach could show. Additionally, we observed that when the real space is empty, ENI provides values close to 0, and this is because ENI is a metric specialized for navigation in VR. On the other hand, our proposed method considers the central table and reflects alignment difficulty, producing larger values corresponding to differences in spatial complexity. These results indicate that our approach is more appropriate for measuring spatial matching difficulty level between spaces, for registering basic geometric information between the similar physical and virtual space. Through this research, we demonstrated the uses of redirected walking as an adjusting term for registering virtual space to physical space. Second, focus on registering an object-oriented subspace precisely. And lastly, we highlighted that spatial matching's priority component should be set considering the purpose of the VR experience. In conclusion, this research contribution can be threefold. First, we proposed an Edge-Centric space rescaling technique for dissimilar physical virtual space registration. Additionally, we proposed SD and SMD for calculating spatial dissimilarity and spatial matching difficulties. Finally, we validated that space rescaling with RTG could improve the accuracy of matching table edges and walls in all 4 realistic space pairs compared to the 1-to-1 scale method. Yeah, that concludes my presentation, and feel free to contact me. Thank you.